And I forgot to hit record. All right, so now we're recording. Welcome to class. I always feel like I need to reintroduce the class for the recording. Um, we were chatting before everyone else showed up about how in a computer science degree, the idea of data structures and algorithms is something that's kind of this long ongoing thing. It's not like you take one class and you're done, you're an expert at it. It's kind of like they sort of dish it out in bits and pieces kind of throughout the degree. Although there are fully dedicated classes. I am not going to try to replicate, a year and a half of learning into a 90-minute or 2-hour time slot. So don't worry about that. But you all are going to help me actually teach the class today. So what we're going to do is we're going to make some breakout rooms where you're each going to study some and not study. You're going to do a little bit of research on some data structures, and you're going to come back and you're going to describe what these data structures are and how they're used and so on. We'll get to that in a little bit. What we want to start out with, though, is something kind of fun, something a little goofy. And we're going to look at some sorting algorithms, but with a twist. There's always a twist. So I'm going to drop a link in your channel. And I'm going to do this on Slack. So look for it in the Code Help channel. Want you to look up the bubble sort video. Actually, let me just go link directly to that one for you. There's the bubble sort. Copy link. All right. So here's the deal with this. You're gonna learn all about how bubble sort works by watching some Hungarian dancers. And so I'm dropping a YouTube link in your Code Help channel. What I want you to do is go hop off Zoom for a minute, and when you're done, come back. So this will take less than 5 minutes. Skip the first 60 seconds of the video because the first 60 seconds is just randomly, dancing around the stage to randomly organize themselves. But what I want you to do is go watch this video. Try not to get the song stuck in your head because it's kind of annoying. But go watch this video on how bubble sort works, and we'll come back in 5 minutes and discuss. All right, so you can hop off Zoom if you want, or you can just mute other audio. But go watch this, and we'll come back in 5. So we'll come back at 11 after the hour. All right, welcome back, everybody. We often get requests for like, could Turing staff do something like that? I think Lita in the front end program used to do a class like this, where she would actually have like little headbands with numbers on them and have the students like just walk around the room, but basically mimic out the different sort of sorting algorithms. We're not going to go into sorting algorithms today. There's a bunch of that stuff written up in the lesson plan. And I made a note in the shared Google Doc that I think Alex posted in the chat. Of some of these other videos to watch. Now you can watch them with the music off if you don't like the music, but I think it's a much more entertaining way to learn how a thing works, or at least see visually how things work. I think that especially if you're a more visual learner, sometimes it can be a little easier to sort of comprehend what's going on by seeing a visual representation of it. So I think that kind of stuff is pretty helpful. Cool. I'm just adding some stuff in the Google Doc here about where we're going to go from here. We got stacks, we got queues, we got linked lists, and binary trees. All right. So what I'm going to do today is split you out into some breakout rooms for a little while. And what I'm going to do is I'm going to make 5 breakout rooms. And in those breakout rooms, you're going to each study one data structure. And then you're going to come back and you're going to teach the rest of the class about that data structure. But before we do that, I want to give a bit of preamble as to why we do this kind of class. Actually, let me just back up a little bit and we'll talk a little bit about like sorting algorithms and so on. Occasionally you will get asked like, how does a sorting algorithm work during a tech interview? It's okay to say like, hey, we don't study that at Turing. In fact, that's a perfectly acceptable answer for just about anything that you get asked in a technical interview, where we legit don't teach it at Turing. If they say, tell me about Rails, and you say, oh, we didn't learn that at Turing. But for topics that we legitimately don't cover at Turing, there's a lot of deeper computer science kind of theory and things like that that we just don't have time to cram into your brain in 7 months. It's perfectly acceptable to say, Turing didn't teach us that. My curiosity hasn't gone there yet, but I want to go learn that at some point. Learning about how merge sort, quick sort, and insertion sort work are the 3 most widely used sorting algorithms in the programming languages that we use. So Ruby, for example, implements quick sort. And so if you have an array in Ruby and you tell Ruby to go sort that array, it's going to use quick sort. Python will use either insertion sort or merge sort, depending on the size of the data. JavaScript will use different things depending on the browser that's actually executing the code. For example, Firefox and Safari use different sorting algorithms, and browsers like Chrome that use what we call the V8 engine will use quicksort or insertion sort. And so at least, watching those videos or something to see like, how does merge sort, quicksort, and insertion sort work would be good to at least visually take a look at. You don't have to go learn the algorithm if you don't want to. You probably won't get asked that in an interview. But for other things around the idea of data structures, the reason that we're diving in on this a little bit is because data structures can make or break a technical challenge for you. There are a lot of technical challenges out there that will work depending on the data structure that you choose to use. But there are implications based on which data structure you choose to use. We're going to go into one of those as an example probably tomorrow during the Big O notation class. And the Big O class will actually be both front end and back end students together. So the big idea that we have around like, why are we spending time on this? You're in the middle of a project, you're trying to wrap it up, you're trying to get your MVP done. Why are we pausing and learning about this kind of stuff? Some of you are already starting to interview. And so we think it's a good time to start at least introducing the idea of, how do these data structures work? Like if you had to go build this kind of data structure yourself, or if you are given the choice of, do you use this data structure or that data structure, which one would you reach for and why? Do you reach for a particular data structure because you're comfortable with it, or do you reach for it because that's the best tool for the job? Kind of goes to the whole, if all you have is a hammer, everything looks like a nail kind of adage. So the hope is that by giving you at least an introductory idea into what these data structures are and how they're used, it's going to differentiate you from other coding programs that don't go into these kinds of topics. We've discussed quite a bit in the backend team about how we could sort of scatter this information all through your time at Turing, so it doesn't feel like we're like cramming for finals and like trying to get it in your brain at the last minute as you're going out for interviews. But we also know that, the more recently you learn something, sometimes the easier you'll recall it when you interview. And so like now is kind of like interview season for some of you. If you need a job sooner than later, you may already be interviewing. If not, that's okay too. But I think it's important to at least know how these things work. And so it really comes down to how are you differentiating yourself during these interviews. I often get asked by students, like, how do I compete with a CS degree? People are going to school for 4 years and they're coming out with a CS degree. They got all this knowledge. How am I going to compete with that? I've gone to Turing for 7+ months. We don't learn everything they learn. So how are we going to compete for those kinds of jobs? And I always tell students that CS degrees are equipped for different kinds of jobs than you are. I think of CS majors as like the blacksmiths. Like if we were all to like go back to medieval times, a CS major would be a blacksmith. They're going to make the tools that everybody else uses to get the job done. Like they're going to make all the gardening tools and all the weapons and all that stuff for other people to do what they do best. And so a CS degree is going to be writing the next cool programming language. They're going to be building the next cool database, or inventing like the next Git kind of thing. But you're coming out with knowledge about how to put all those tools together and go build really cool applications. Like I can pretty much guarantee nobody coming out of a CS program is building the kind of stuff that you're building right now on consultancy. They may build like a smaller scale app similar to what you might have done in Mod 2, but they're certainly not going to have done like a full blown microservice based, SOA kind of application like we've asked you to design here. They probably have never even heard of OAuth, much less implemented it. You're coming out with a lot more knowledge about how to fit these pieces together and do something useful with them. And so I often tell students that they shouldn't, but it's not my place as an instructor to tell someone how to feel, or it's not my place in life, rather, to tell someone how they should feel. But I would say it's important to recognize that you're not competing directly with a CS degree in the same way. Like they're coming out of a CS degree with much different knowledge than you are, and that's okay. They're, like I said, they're going to be equipped for something completely different. I've interviewed CS grads in the past. They have no idea what Git is. They have no idea what Agile is. They've never used something like a project board. But they're going to be really smart, and they're going to have like all of these ideas about like how to optimize code. You're also coming out also very smart, but you know how to build like full-blown applications, and you're understanding like how all these things sort of fit together. So I would say there's no direct competition in that sense. So I just want to be really upfront about that. Cool. I appreciate folks like adding stuff into that Google Doc for kind of later study. I do recommend like go back and check out some of these links. Some of these links are going to be really good. There is a binary tree gist that I've made. There's also one for a linked list and some other ones that I've been working on too, but we'll get into that a little bit. So what we want you to do over the next little bit, I'm going to pause for some questions before we do this. But what I want to do is break you out into breakout rooms where each breakout room is going to go study one kind of data structure and then come back and give us like a brief introduction It doesn't have to be like full slide deck, or it doesn't have to be super polished, but I'm going to give you a list of questions to kind of go learn about as a small team. And you're going to come back and just present your answers to that. I would like everyone's involvement. So please know, working on your projects, like work on this. And then once we get done, so you'll notice in that Google Doc, I've got arrays, stacks, queues, linked lists, and binary trees. One of the ones that we don't get into are hashes, because I'm actually going to answer these questions about hashes for you at the end. So we'll dive into like what a hash is. But in the Google Doc, what I would like is for each group. So let's do this. We're going to do like arrays and stacks. I'm going to give you each a different sort of page in the document. And you can all go kind of add your own notes to that as you research it. So don't start adding stuff yet, because I haven't told you which teams you're going to be in. But these are basically the data structures that we want to go learn about today. Before we get into that, what questions can I answer for you? Let's take like 5 to 10 minutes and just talk about like what kinds of questions do you have so far about data structures, algorithmic thinking in general, anything like interview related along that topic. Let's open it up for some questions. Yeah, Mike, what do you got?
So it sounds like a lot of our work will be going to code bases that are already established. When do you think data structures will come into the conversation in our career? Like, if the database is already established, would it just be like a refactoring a database, so to speak, or like how have you seen that in the workplace come on the work table, so to speak? Yeah.
Yeah, that's a good question. I would say that with a lot of entry-level roles, you probably won't be interacting directly with a database, or it would be less often, because a lot of these code bases will already exist. You're going to have some kind of pre-existing app or service or whatever that you're going to be jumping in and helping with. As an entry level dev, you can make recommendations like, hey, if the table had this, then we could do this or that. But it's going to be someone else's job to actually go implement that. Now, later in your career, once you have that kind of experience, they're going to come to you and say, hey, Mike, what do you recommend we do here? And now it's going to be on you to make those recommendations. And so as you sort of gain that seniority in your career, you'll have more like influence and decision power around how things are done. But early on in your career, you probably won't. When it comes to the idea of data structures and how those get used, this is really like prepping you for interviews, because they may ask like, how does a hash work? Or when would you use a linked list versus an array? Those kinds of questions, those may come up in an actual interview scenario. And a lot of interviews really come down to just the problem solving of, I'm going to give you something novel to think about, and how are you going to go figure that out? And so most of what we're going to be looking at today is just prepping you for the technical interview. And also some of the knowledge that you're going to learn today about these data structures will help when sort of breaking a technical challenge down into parts and trying to decide how you want to solve it. Should you use an array? Should you use a hash? Should you use a linked list? That sort of thing is mostly what we're going to be looking at today. Cool. Thanks for asking, Mike. Max, what do you got?
I have a question kind of on maybe similar, but implementation of some of these. So I know like at the end of mod 1, we started doing like more complex computation kind of things within Ruby. And then by mod 2 and now in mod 3, it's like, we just use some multiplication and addition. Like end of the day, we don't need any of this other stuff. Is that similar to this, that when we are going to be using like linked lists or binary trees or any of this, it's going to be mostly in plain old Ruby or like Python as opposed to on a Rails app or something like that?
Well, I mean, Rails is
like...
Yeah, no, it's a fair question. If I understand right, like I would say in like Rails is written in Ruby. And so if there's something about how you're manipulating the data in Rails, you could still go, interface with these kinds of data structures. Now, of course, arrays and hashes are already built into Ruby, as well as Python and most other languages. They already have the notions of these things already built. But not all languages. Like some really low-level languages like C, for example, they don't have the notion of a hash. You actually have to go build that yourself if you want something like a hash. But that's also why we have like these higher level languages where these things get implemented for us. So you can still build like a Rails app or a Python app using like Django or Flask, like the respective frameworks. Flask is like Python's version of Sinatra, and Django is like Python's version of Rails. But you can certainly go implement like lower level Ruby code or Python code in those respective frameworks to do these kinds of things. But again, this class is really going to set you up for doing like technical challenges, where it's like an on-site interview where they're like, hey, you know, how many months in the 20th century started on a Sunday? Like where the first day of the month was on a Sunday. You have to go figure out, well, what data structure am I even going to use to like try to figure that out? You know, do I use a hash? Do I use an array? Do I put it in some other kind of data structure? The data structure you choose could influence how long that algorithm takes. In my career, have I ever actually implemented a linked list and binary tree? Yeah, a couple times, but not very often. Mostly we're going to be using what's built into the language or built into you know, a framework of some sort, or we're just pulling stuff out of the database. And so how the database does it under the hood, that's for the CS grads to like go figure out. Like, you know, there's a data structure called a B tree, for example, and that's used with indexing in a database. You'll probably never get asked what a B tree is. You may get asked what a binary tree is, and a binary tree and a B tree are very different. But a CS grad, they're going to know what a B tree is and how to actually go write code that implements and uses a B tree, which is the most popular, widely used way of doing indexing within like Postgres and MySQL and other relational databases. But that's not something that you'll ever get quizzed about. I mean, if you want to go there, you can, but you're not going to get asked that kind of stuff. Cool.
Thanks.
Good question so far. Yeah. Let's take like a couple minutes. Anyone else have questions? All right, we're gonna start with a quick little palm break. So we're gonna take like a 5-minute coffee break. When we come back, I'm gonna have some breakout rooms made for everybody. And in those breakout rooms, I'm gonna give you like 6 or 7 questions to go research. And so you're gonna have to divvy up this work across everyone in the room. And you know, if it works better for you to like just mute all your audio and go read up on this stuff, and then like talk amongst yourselves, like who's going to go look up which part of this, or how are you going to research together, and then you know, do like a quick DTR of like, I like to have my audio off while I'm like going and doing this thing, or yeah, I like to have some discussion to like figure this kind of stuff out or bounce ideas off each other. But I'm going to give you a little template in that shared Google Doc about what do I have? I got like 7 points, I think, that I want you to go learn about. And then when we come back from that, I'm going to go through each of the groups, and you're going to just hit on some of these high points here. And so it's not meant to be like a full blown thing. I'm only looking for like a couple of minutes maximum to like kind of answer these questions. But by having all this stuff in that Google Doc, you'll have it to kind of come back and reference. Again, I think that this is really important study material. And I just put the link back to the Google Doc in there just so that you can all get that opened up and look at it. I think this is really important study material to get through interviews. So really want everyone's involvement here. So let's take a 5-minute palm. We'll come back at 9:35. So we'll come back at 35, and we'll get the breakout rooms and so on made then. All right, welcome back from break. Cool, just having a quick look over chat. Yeah, did you bring enough for everybody? Cool. All right, so I made some breakout rooms. The name of your breakout room is going to be which data structure you're going to look at. So In that Google Doc, I've added a bunch of stuff and I've highlighted it here in the Google Doc. I will also put it in the Zoom chat for you as well. But these are the questions that I want you to kind of research and read about. So explain this data structure to someone using non-technical terminology. Like think of like a friend or a family member who knows absolutely nothing about computers. How would you explain this to them? And I've got reasons for like, this, and I'll talk about that a little later. But also describe in kind of plain language, how would we add, find, or remove data from that data structure? What does that process look like? Can you find information about why this data structure was made? So I recommend looking on things like Wikipedia for like when was it invented? How long has this thing been around? Why did we come up with the notion of this in the first place? Like, why is this helpful? Do variants of this exist? So like for linked lists, there are several different kinds of linked lists. If they have variants, like why do we have variants? Like what's the difference there? Or if you can't find a variant, like why do you think that is? But the main two questions that we really want to get out of this are these two here that I've highlighted. What is this good for and what is this not good for? Like what does this data structure really excel at? And what would be a use case where like if I chose this as my data structure, it would be like a really bad idea. And so try to think of those kinds of things. Is this built into Ruby? And if not, how could we build it ourselves? Like what would that look like? And then try to find like a common technical challenge for that particular data structure. So you can look on LeetCode, HackerRank, Code Wars, other, but want to start giving you some ideas around like, hey, if you really want to dive in and see what a typical interview challenge would look like using a linked list, this is what you would, or here's like a place that you could go study. So these are the questions that we want you to answer. So each of the groups are going to go answer these. I'm going to give you half an hour for this. And I mean, advocate for yourself if you need a palm break in there. We're going to come back at 10 minutes after the hour, approximately, depending on when we get this started. I'm going to give you half an hour to go research these things as a group. And then we're going to come back and I want to hear from each group. So figure out, everyone should be adding notes in the Google Doc, but who's going to talk about it when you come back? Because we're going to go through all 5 groups. And then when we get finished with that, I'm going to talk about hashes and how hashes are used and how they operate. Who has questions about what we're about to go do? Everything's perfectly clear. I don't want you to get into the breakout room and the first question is, what are we supposed to do? Everybody super clear? That never happens, yeah. I think I did it twice yesterday in our staff meeting. It's like we got put into a breakout room, like, wait, what are we doing in this breakout room again? All right, if you're all clear, I'm gonna give you half an hour. So we're gonna come back at 11 minutes after the hour. So go research these things. Look at the name of your breakout room. It'll be at the top of the Zoom window, and that's gonna be the thing to go research, okay? All right, we'll see you back in a half hour. Cool, welcome back from your breakout rooms. Let's do a quick palm break. We'll come back at 15 after the hour. Sound good? We'll see you back in 5. Resume the recording, there we go. Cool, let's start with our array group. So we're gonna go to Sydney, James, and Phil. Teach us all about arrays.
Yeah, so should we just like work down top to bottom on those checkpoints?
Yeah, let's start. Let's start with like this simple sort of analogy explanation of like what it is, and then go into like some trivia about it, like when was it made, how was it used, stuff like that. What's it good for, and so on. Yeah.
Okay, yeah. So consider you write a list of your top 10 favorite movies. you have just created an array where you're using the numbers 1 through 10 and you are referencing a movie on the list. Or you could consider like the periodic table of elements. That's an informative array of elements like ordered by number. And then you can add items. Typically you would add them to the end, especially like the periodic table of elements, and you can edit them. And everything you're referencing would be by index, or you could actually look up like the name, the line item itself. And yeah, why this data structure was made. The first array, at least in like for computer programs, was written in 1945. It was for the first like stored program computer, and it exploits memory addressing. So arrays are like every line in an array is what am I trying to think? Is indexed based on like the memory's address in the computer. So it exploits computers, I think, for speed and runtime. I think.
All right, what's next?
Sydney, yeah.
So like, do variants of this data structure exist? Why or why not? So yes, there are other variants, but not in Ruby. So in Ruby, arrays can hold all other data structures, where in other variants, they cannot. So that was interesting to learn. Did you want to do yours, Phil? And then I'll jump back in.
Yeah, sure. So as far as like what is an array good for, so kind of like James was saying, it stores multiple values like to a single variable. So it's a really, because everything is stored like next to each other in memory, it's very like efficient when you go to access elements of that array. So I think like an example from Ruby is like you can call methods on an array and it's more efficient than like enumerating over it. So like if you say, hey, what is the length of this array or the size of this array? Like it's doing less work. The computer is able to just like spit back in, I guess, binary that like the length is X. Whereas if you were to count it, it would act like a Ruby enumerable would actually like go through and count all those things. So it's like a benefit that like that data structure can like return information about itself and its elements quicker than if we had to enumerate over it. It's like a good option when you know how many elements you're going to store. So this is something that I wasn't aware of, like how Ruby implements an array versus like the data structure itself. Like every time you add something to an array, the entire thing gets recreated and stored in memory. And maybe Ruby's implementation is a little different. I'd be curious to hear you and talk on that. But it seems like it's really good when you know how many things you're going to be storing, or like if the things are closely related. But if you're storing millions of things and like you don't know how big that could get, it might become less efficient as your program grows. And then, yeah, so other things on like, why is it not a great, when would it not be a great option? It's mainly just that it's not super memory efficient because the memory is reserved. So like essentially if nothing is stored at a given index, when you define an array that is like 1 million elements big, but you only add one thing, you're reserving space for the million, like up to the millionth index, even if they're all nil. So it's like not a great option in that case. Yeah, that's about all we had on those two questions.
Yeah, thanks. And yeah, some programming languages have fixed length arrays and some are more dynamically allocated. And some programming languages, when you say, hey, I want to make an array, it'll say, okay, let's give you like 1,000 elements. Like, I don't know how many you're going to need, so I'll just reserve a chunk of memory. But as it starts to fill up, the interpreter will be like, oh, shoot, that's filling up. Let me, let me go allocate new memory. Going to copy all that stuff into that new block and give you more space. And then sometimes as you remove things, the interpreter's like, well, you don't need that much room, so I'm going to like go free up some of that memory. And so there's a lot of stuff happening under the hood sometimes in these high level languages. You'll also hear the term like vector in some programming languages that will talk about like, dynamically sized arrays versus fixed size arrays. So a lot of compiled languages will be fixed size, where you say like, I'm going to make 100 things. And if you try to like add one more thing, it'd be like, you said you wanted 100. And it won't grow beyond that, which are good and bad for various things. Lots of pros and cons there. Cool. All right. Anything else about arrays that you want to tell us?
Yeah, so we did have, you kind of just covered this with like, if they're built in Ruby.
Yeah, sorry, Sid.
No, you're good. So yeah, they are built into Ruby, and then like just like Ian said, Ruby does a lot of the hard work of like managing that memory, expanding the size like when we need it, and compacting it when we delete things, which is really cool. And then when we were thinking about like how we would build this ourselves, we thought either a hash could be utilized where the keys would be representative of the index positions, and then the values would be like the data types. Or also like a string has some of this some similar array capabilities as well. So we thought maybe a string depending on what we were trying to do.
Awesome.
Yeah. Another thing real quick too, I was thinking like a non-technical way to describe an array. A book is an array where you're organized like by page, and every page is a nested array of organized by words. You could reference a word on a page like nested deep.
It's good for the code breakers. Go to the 5th page and look for the 4th word in the 3rd paragraph, kind of thing. Yep. All right, awesome. Thanks for that. Yeah, there are a ton of interview challenges that will use arrays. Arrays and hashes are probably the 2 data structures that you'll use the most in technical challenges. So being aware of like what they are, how they're used, how you can kind of manipulate them will be really important for sure. Awesome, thanks. Let's go on to Stacks. And Stacks is going to be Adam, Eli, Joe, and Robert.
So I can talk a little bit about just what they are very broadly. They are, it's kind of like if you have a stack of books and you put the first book down and then you put the second book down and the third book and so on. In order to access those, you can only pull from the top of the stack. And then you pull the top one and so on back down. And a practical example with this is the back button on your browser, where you're taking the URLs and you're pushing them onto it. And then when you go back, you're pulling it back off. And then that's how, I don't know if you've ever wanted to go back to a page, but then you realized you hit back too much and went forward and clicked a different thing, so you can't actually go back to the other one. That's kind of one of the tricky things about Stack. And so that's basically what they are at a non-technical level.
Yeah, to add a bit to that, it follows the LIFO or LIFO principle. So last in, first out. Another like explain it like I thought, like on 5 example. You could have your hiring management practice be a stack. So if you're looking for someone to fire, you fire the person who was last hired. That's treating your staff as a stack, if that makes sense. Or Philo, yeah.
Yeah.
Also, it was invented in 1957 by Frederick L. Bauer, who also invented the term software engineering. Fun fact.
Very cool. I like thinking of it as actual stacks. So when I think of stacks, I think of a Pringles can. So the first chip they put in is the last chip you can take out. FIFO is not a stack. First in, first out will be the queue, and we'll get to that in a minute. Cool. What else do you want to tell us about stacks?
Cool. I can go. So I'd say like they're really good for temporary storage, I guess. So it's like if you're iterating through something and you need to kind of compare or like match things, you can add things to a stack and then basically pull out the last element as needed for, I guess, whichever whatever thing you're doing. And I guess this is kind of a little skipping ahead, but there's this leak code problem that we found. It's basically you're comparing, you're seeing if the string provided is like giving you valid parentheses. And so you're kind of iterating through this collection and storing the last element in a stack to kind of compare it next to like your next element in your iteration. And I guess, yeah, kind of like a to-do list. So it's like you're processing these elements and generally using pop, I guess, to pop that last element off and then kind of use that as your comparison.
Yeah, and so stacks are very commonly implemented using arrays where we're just shoveling onto the end and we're popping off the end as well. Yep.
Can I ask a question? Can you
do.
use a string as a stack? I mean, I guess not really, probably.
Well, at a deep technical level, a string is just an array of individual characters. And in some programming languages, it's terminated by like a nil byte or a null byte at the end, but it's effectively just an array of characters. That's how low-level languages like C actually implement a string. It's just an array of characters, but it's a fixed size, and so it can only be that big when you're done.
And fact check me on that, Ian. My thinking with a stack is like with an array, the look matters. Like this is an array. This is what it looks like. Whereas with a stack, the feel matters more. Like to be considered a stack, it's dependent on the behavior. So like if you meet these 5 behaviors or criteria, you are a stack. Whereas with arrays and hashes, it's much more like if this is your structure physically, you are array or hash. But a lot of things can be a stack depending on if they meet these behaviors.
Yeah, that's a really good point. So stacks and queues are typically implemented using arrays, although queues can use linked lists as well. But it is about the behavior of it because we're only dealing with the end of it. With an array, we can kind of iterate over the whole thing and look at any point, like what's the 5th thing in the array? But when you have a stack, you don't really say like, what's the 5th thing in the array? Or what was the first thing I put in the stack? You're only dealing with the last thing because that's the last thing you put in and that's the first thing that you're taking back out. And so with a stack, it is absolutely about the behavior. How it actually gets implemented can be a little bit different. I should back up and say stacks and queues could both be implemented using arrays or linked lists, but we'll get into that a little bit deeper as we go. Cool. All right. Anything else about stacks?
For what it's not good for, can we just say normal things that doesn't need to be implemented in that manner?
Yeah, I mean, that's fair. Or I would probably summarize it and say anytime you need to access anything else within the stack besides the last thing.
Right.
Like if we had a whole bunch of people lining up to get into a venue or something, you know, actually, no, that would be a queue. Would be another good example of a stack. I mean, if you think about like how tennis balls are sold in a tube, right? You can only take out the last tennis ball that they put in. You can't really reach below that and grab one from like the middle of the stack. So yeah, I would say anytime you need to access anything besides the very last thing that you put in there, you wouldn't use a stack. Stack of plates is a great example too. If you go to like a buffet style restaurant where, you know, they load up the stack of plates and it kind of sinks down into the counter, you can only take the top one. So yeah, cool. All right. Anything else about stacks? Cool. The valid parentheses programming challenge is probably the most popular stack question. If you get asked that, you absolutely want to use a stack for that. Cool, let's move on to queues, and that's going to be Catherine, Isabel, Mike, and B.
Yeah, so for a non-technical explanation of queues, we're all very familiar with queues. It's just kind of it's like a sequential ordering of data. So we can think about things like if we're lining up for a movie, the first person that queues up with the first person that goes into the movie. And then in the way that we see them in Ruby, they are used in arrays, but in Ruby we actually have double-ended queues, so we can do like shift and unshift. And in terms of like why this was made, it's predominantly used in industries where having a sequential ordering of things is really important. So like operations, I'm sure there's many more than just operations, but like for a smaller example, like a printer, like printing out the pieces of pages in sequential order. And in terms of why it was made, so that was that there. Team, catch the next one.
Right. So I'm not super sure about this one, but for variants, there is simple queues, circular queue, priority queue, and DQ. I wasn't, I'm not super sure that was what you were looking for there. Sorry.
Yep, those are good examples.
Okay, cool. And somebody else, apparently my voice is going.
You're good. So queues are used for when things don't need to be processed immediately, but need to be in some kind of sequential order. So two kind of real life examples would be a call center where the first person who calls is the first person who gets the next representative. A printer, the first thing you click to print is going to be the first thing that comes out of the printer. And then just this last bullet point here, I think is a pretty good example of whenever it would be useful. There's one resource and then multiple objects that need to use that. So it's like a waiting list. And then on the other hand, it's not really good for using things that need to be kind of all done at the same time. And a queue does tend to take more time when you're going through a long list of items that need to hit that method or whatever it is, it can take a longer time.
There is a queue class that actually is like inherently built into Ruby, as well as you could just use an array and using similar functionalities of like push, pop, unshift, and prepend to work with that. And yeah, and then we did find a tech challenge that we have linked that we went over really well, if he wants to also talk about it.
Cool. We'll let people read that on their own time. Yeah. So there are different kinds of queues. I've implemented a lot of queues in the workplace, especially for things like background workers, where you've got like a whole bunch of things batched up that you need to process. You just keep loading it into a queue, and then something's reading it off the front. That's also where you can get into like priority queues, whereas like, you know, I've got these little bits of work that need to go out, but this one's more important. So don't wait for all the other ones to go out. That could be things like if I need to send an email for a password reset, that should probably take a higher priority than like sending out a newsletter. We need to get that email password reset out before we handle like millions of other emails. And so we may pause like pulling off of one queue in order to pull off a different queue. Sometimes that can be implemented using multiple queues, where the software just knows like, hey, if anything shows up on this queue, it's more important. I need to go handle that first. Sometimes the queue itself will have like a priority level, but that means then that whatever's looking at the queue kind of has to look all the way through the queue to say like, oh wait, this one's more important. I need to go handle that one and pull it out of the like partway through. So so that would be like, you know, if people are lined up to get into a venue and, you know, the bouncer's like up there at the front of the line and he's looking down the you know, who's in the line, and he spots like some celebrity, be like, hey, you know, you come to the front of the line, you get in first. That would be kind of like a priority queue. But again, they're sort of like looking through the whole queue in order to pull that person out, as opposed to having like a separate VIP line. Would be a different analogy there. All right, awesome. Let's go from that and let's go into linked lists. That's going to be Aiden, Grayson, Liam, and Sam.
Yeah, linked lists are very similar to arrays. In some ways, they're more efficient. So arrays, like kind of the first group said, need to be recreated every time they're altered, and they also take up one space in memory. Example of this would be if you went to the movies with your friends and you had a certain number of seats in the theater and then more friends showed up, you'd all have to move to a new part of the theater with enough seats. Where with linked lists, they would have their spot, and then when more friends showed up, they would sit in other empty spots, and then the previous friend would know where the other friend is sitting. So yeah, so this just makes it more efficient. And then if you have like a huge data set that's always changing, you don't have to keep like hitting a new part of your memory every time to like get a bigger space.
That's a great analogy.
Yeah.
Yep. The other interesting thing there is you can insert someone in the middle where we can't with an array. When you have an array of like 100 things, you can't say like, oh, go put this like exactly in the middle. You basically have to like cut the array in half, go allocate new memory, put the thing in the middle, and then like copy the other half. Where in a linked list, because they're all node based, you can just say, I want to insert this node in the middle. So when I think about the differences between arrays and linked lists, I think of like, are these houses in a neighborhood, or are these like the houses of like the kids that go to my kid's school? Like they may be kind of spread all over different neighborhoods. And like one house isn't necessarily the next door neighbor of the next house. But when we look at a subdivision would be like an array because everything's right next to each other in memory, where when you're building nodes for both linked lists and binary trees, those nodes can kind of be built wherever you want in memory.
Yeah, touching on to what you just mentioned, Ian, I think at this point we could compare other data structures like, I guess, a stack compared to a stack where you have to start from the top. With a linked list, you can get past the top and not edit the top. You don't have to edit the elements at the top, or you can keep on going until you find what you need to and change or insert a node into there. And as opposed to a queue where you'll probably have to start at the bottom being the first one in, similar to a stack. And with the array that you just mentioned, that would be a case where you have to insert everything into an array in the middle. I think you have to offset everything else after by one, and that's just not as efficient. And I think a good use case for single linked list would be, we talked about an undetermined amount of elements to add into a container. You can just push an extra element onto the end of the tail. And just to talk about the structure of a linked list, it will compose of a head and many nodes being in between, and a tail. And actually the head and the tail are nodes that do hold elements too. And I'm not going to talk about double linked list just because that's what Grayson will carry on forward, but a singly linked list will be starting from the head. You can only go unidirectional starting from the head. So I guess another difference would be in an array, you can jump right into the middle also if you know exactly which element you need to get to. But the difference between that and a single linked list would be that to get to the middle or the middle element, you have to start from the head and keep on going forwards. And I'll leave the variance to Grayson.
Okay, so the only variant of this that we could find was a doubly linked list, which is just a linked list where a node not only stores a pointer to the subsequent element, but also the prior one. So maybe the second element in the list knows about the first and the third, and this allows you to traverse both ways, which means nodes near the end would not necessarily be more computationally intensive to reach. So if you wanted something like the third place from the end in a single linked list, you'd have to go from the beginning all the way to that third from the end. Whereas with a doubly linked list, you could start counting at the end and go backwards until you hit that, which would be much faster. However, in terms of write speed, it's slower because you now have to update two other nodes with the position of your new node, because the pointer is basically being stored in two places. And then we actually found on some website that the read time for a doubly linked list was O of 1, which doesn't really make sense. And I'm not sure if that website was the most reliable thing, but yeah, I don't know about that.
No, so O1 is what we call constant time lookup, which means I need exactly one operation to like go find what I'm looking for. An O1 would be like if you're already on that node, then like you've got exactly what you're looking for. But if you've got all the numbers from 1 to 10 in a linked list and you need to go find the number 7, you have to start at the beginning and you have to like keep traversing through all of them until you get to the node that has that value. So I think of linked lists like a chain, like each link leads to the next link. And you have to go in order to like, hey, go find the 10th one. You got to start and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I've got the 10th link of the chain. Where in an array, you can just jump immediately there. And how the array jumps immediately there is because everything in the array is the same sort of memory size. And so when you say like, go to the 10th thing, it goes, well, how big is everything in the array? Let's say it's 8 bytes and you want the 10th thing. So 10 times 8 is 80. So from the beginning of the array, I'm going to move ahead 80 bytes. Now I'm already at that memory location of where that next thing is that you wanted. We're in a linked list because the nodes are kind of potentially scattered all over memory. It has to go from one to the other to follow all those nodes to get there. Cool. All right. Yep. Anything else about linked lists?
Oh yeah, we just had some tech challenge questions that we were able to find. Just for example, I suppose, how do you find the middle element of a singly linked list in one pass? What is the difference between an array and a linked list? How do you check if a given linked list is a palindrome? And how do you reverse a linked list?
Excuse me, folks. I'll be right back.
Some fun trivia.
When the teacher leaves and everyone starts throwing music fans and stuff, and like this goes absolutely bonkers.
Does he have wireless headphones though?
Yes, he does.
God, I'm so glad he's gone. Jeez.
Liam, what's the trivia? I really want to know.
Oh, do you really want to know?
You said it was fun. You said it was
It is really fun.
It's super fun. You know, linked lists were developed in the 50s by Alan Newell, Cliff Shaw, and Herbert Simon. Sam, take it away.
Give it up for Cliff Shaw.
Who dat?
Sorry about that. All right. Yeah, the interview challenge about find the middle element of a linked list by only doing one pass is it's a type of challenge that we call fast and slow pointers. So that'll be the hint there. Let's move on to binary trees.
Oh, we just did this one, Ian. You missed.
Oh,
it.
did you? You did the whole thing already?
Binary trees are pretty fast, so.
I see what you did there. All right.
Yeah, so binary trees, like linked lists, are also like node based, where each element stores like a reference to other elements, and you start with like kind of the root of the tree, and then if you're doing a lookup, like you would say, okay, so this thing that I'm trying to find in the tree, you're going to compare it to the root, and if it's larger, I'm going to look in the left branch, and if it's smaller, I'm going to look in. If it's larger, I'm going to look in the right branch, and if it's smaller, I'm going to look in the left. And then you just like go down the branch and keep comparing it to each element until you can make no more comparisons. Essentially, insertion works the same way, and so it's a node that has a pointer to two other elements. Although there's variations where you can have more than 2 pointers. And then when you get to like the leaves of the tree, that's at the point at which you have like no more references and nowhere else to go. Yeah.
Yep, that's good. Yeah, basically the very last nodes are what we call leaves, where everything else is kind of a branch node. And at the very end, the leaf just points to like a nil usually. So you have like a left and a right, and they just point to nil as the default. Cool.
And there are like lots and lots of different kinds of trees. But one thing that makes sense in my brain about why you would use one is for like compression algorithms. And so I'm gonna share a screen just for a second because I drew out a little thing. So if you're like looking at this string of 4 letters, in binary, it will look something like this, where it's like a lot of characters. So you could make a binary tree that would look like this with your root, and then on one side you got A, one side you got Z, and this is kind of the coding for that. And this says how they point to each other, which I don't quite understand. But basically then, in order to write this AAZA, you just have to write the root in the binary tree, which should be, this is an A, this is an A. Go to the right, this is a Z, and that's an A again. So you can see that if you construct your tree and you like want to reference each thing multiple times, running to the root or navigating by the path is can be much faster.
Interesting. I haven't heard that one myself. Cool.
And I can jump in. The inverse of where these are not so good is if you are writing lots of data. So it's kind of like the opposite on the linked list side. If you are writing and removing a lot of data because of all the dependencies of this, they're really slow. Whereas if you have it built and you just need to reference it often, it's really quick.
Yep. And databases are kind of the same way too. Some databases are faster at reading than writing. Some of them are faster at writing than reading. So it really depends on, you know, where you need the performance. If you need a database where you're just like throwing in tons of stuff and you need to just get it in the database faster, you would use one kind of database, where another type of database is like you're going to be reading that data more often, than you would use something that might be more tree-based, because finding that data is going to be extremely fast as opposed to writing it. Yep.
And we did find like a Ruby example. I linked a Medium article in the thread, cool. But just as like a bigger picture, I kind of imagine you had like a node class, like everyone's talking about like these node concepts. And say when it an instance of it gets instantiated, it takes a value. And then because of that value, it's going to decide whether it's going to go on that right or left, depending on its value compared to the root or compared to whatever branch it's going off of. And there's kind of like that base root that has to be decided when you're constructing it. And then each added instance is going to branch off of that depending on its value, where it's going to go. But yeah.
Awesome. Cool. All right. Anything else about binary trees?
I guess there's many examples on all of the websites to practice with this. But there's also, if you look at the Mod 1 extension projects, the Date Night project is building a binary search tree. So if you want to do it Turing style, that would be a good place to start.
Mm-hmm. Yep. Awesome. Cool. Well, thanks everyone for diving in and doing a little research on these things. Again, the knowledge coming out of like what these things are, how they're used, especially for common interview challenges, will give you kind of a bit of a head start in interviews. It can also really differentiate you and set you apart from other people applying for that job that, you know, come from other programs or other boot camps that don't dive into this kind of knowledge. But my job as an interviewer is just to find out like, what is your level of knowledge? And if you don't know these things deeply, you know, that's okay too. It's just my job to find out what are your limits, and then are those limits okay for what I need on the team? So I would say it's important to note that you don't have to be an expert at all these things. You don't have to memorize this entire gigantic document. We're up to what, 14 or 15 pages or something in here. You don't have to memorize everything in here, but having an awareness of what these things are can have a big impact on how you approach technical challenges. because a lot of companies, they're still using like the leak code hacker rank, like, you know, go work out a quick little algorithm that does just a little piece of work. They're not looking for like a full-blown Rails app kind of thing. Although some companies will say, like, you know, part of our interview process is that you're going to go build a little mini Rails app, but those are less common than just, hey, you know, how many, you know, like the problem that I mentioned at the beginning of the class, like how many months in the 20th century started on Sunday? If I give you a little bit of information about what day, you know, 1900 starts on, like January 1st, 1900 was a Monday, and knowing how to calculate a leap year and knowing how many days there are in each month, how would you actually kind of work through that? Would you use a data structure? How would you make the loops? And that's really just getting practice of like the pseudocode of how would I code this kind of stuff up. So I would really recommend, like, as you're looking through these data structures, try to figure out what would the pseudocode be? What would the steps be to like go add, find, and remove data from that data structure? What would those steps actually look like? And write those steps in a way that you can describe them to somebody non-technical. So that, you know, you get a good sense of like that you're not thinking about it too deeply, I would say. Cool. Any questions on these so far? And then I'm just going to do like a quick intro on hashes. No questions? All right, so if y'all want to like take notes, I'm going to kind of power through these questions for hashes and talk about what a hash is and how they're used and so on. Hashes were invented in 1953, and they were called associative arrays. When we think of what a hash actually is it's based on a mathematical principle of trying to find unique data using using kind of a lookup table. And so sometimes you'll hear these referred to as hash maps, hash tables, or just map. Associative array. Python uses the word dictionary, which I think is probably the most apt name, because when you think about what a dictionary is, you look up in a dictionary and go, oh, the definition of this word is such and such. I didn't have a dictionary, I had a thesaurus. I lost my thesaurus one time and I couldn't tell you how angry I was. So I had to throw at least one dad joke in there. When was the last time I got to tell you a dad joke? Come on. But when you think about like what a dictionary is, you're jumping immediately to that value. Like I can look in here and go, oh, okay, the definition of whatever. You can seek immediately there. Now, I may have to go into the dictionary a little bit to try to find, okay, well, that word starts with I. So let me look through here and find the I's. Now that I find the I, now I'm going to go find the word infamous and go find, you know, the definition of, you know, corrupt, degenerate, and nefarious and villainous and, you know, and so on. Wrong book, but you get the idea. With the way that hashes are used, now that we have learned a little bit about these other data structures, a hash is actually an array of linked lists under the hood. And so the way that a hash is implemented is the key that you're storing has a value. And so like hash maps, hash tables, dictionaries, all these things, they're just key value storage. The key is put through something called a hash algorithm. Now, the hash algorithm is just a mathematical formula that takes that key and tries to come up with something unique about that key. If I were to write a very simplistic hash algorithm of all of your first names that just return the first letter of your name in lowercase, well, Adam, Aiden, and Alex would all end up in that same category. They would all collide because that isn't unique enough. If we did the first two letters, they would be unique enough. And I think so would everyone else in the class. So except for Sam and Sandra. So 2 letters wouldn't be enough. We'd still end up with a collision. So when we talk about hashes, we talk about collisions and how do we mitigate those collisions. And so the actual formation of the data structure is you've got a number of these buckets that these things get put into. And ideally, everything is so uniquely created that there are no collisions. And so everybody gets their own bucket. So when we talk about lookup time, we say that it's constant lookup time because just doing this math algorithm is like one step. And that math algorithm tells you which bucket you're in. And then that bucket is a linked list with only one item in it. And so when you look into that bucket and you look at the head node of that linked list, that is the thing that you're looking for. And so it's effectively one total operation of like how to go find that data. When we talk about collisions though, like let's say we take the first 2 letters of everybody's name and that determines which bucket you get put into. Well, Sam and Sandra collide because SA, it's the same bucket. And so then what happens? Well, what happens is, you know, the first name, let's say Sam is in there first, Sam gets put onto that head node of that linked list. But then when we try to put Sandra into the hash and it comes out as SA as our representation for which bucket it goes into, what happens is Sam actually gets bumped and we actually prepend another node in front of Sam. And so now the first entry in there is Sandra and the next one is Sam. So the next time we have to go find Sam, we do the same kind of mathematical process. When we say, go get this thing out of my hash, it does that hash computation again on the key and says, okay, well, that comes back with SA. So now I go look at SA and it says, well, you wanted Sam. So now I need to go look through all of the nodes in this linked list until I find Sam's node. And then I find the value of that node and return the value. Well, now it's no longer a constant time lookup for Sam or Sandra because we don't know how many things are going to be in that linked list, because a linked list, we have to iterate over everything in that list. And we start at the head node and we just keep walking down that linked list until we find what we're looking for or we get to the end of the list. And so in that case, we say, well, most of the time it's one operation to go look something up. The implementation of it differs a lot between programming languages and how they get implemented as far as how many buckets you're given and what sort of hashing algorithm is used. The combination of the hashing algorithm and the number of buckets will determine the uniqueness and how often these things collide in memory. And so from there, then we say, well, because almost all the time it's an O1 lookup, we just say it's O1, but we say it's an amortized O1 lookup because most of the time it's going to be O1. Almost all the time it'll be O1. So why was the structure made? Well, the structure was really made because we wanted to have like a key and a value where we could look something up based on a name or a nickname or a label of some sort, where we didn't want to have to remember, hey, this is a data structure about my student and their address is in field 6 and their first name is in field 2. And if you want their phone number, that's in field 9. Well, now you've got to remember those numbers. And later on, your programmer's like, wait, which field had the phone number in it again? Oh, number 9? Oh, okay, whatever. But then if you want to add like other things, they would always have to be at the end. And so things may be out of order. It's like, oh, wait, we needed their middle name. Well, we can't put that in the, earlier in that data structure now, because now the phone number wouldn't be field 9, it would be field 10 instead. Now we got to change a bunch of code. And so these associative arrays were made then where we associate the value of what's in the array with a label of some kind. And so they were first invented called associative arrays. In PHP as a programming language, they actually still call them associative arrays. Other programming languages, though, they're using like hashes, hash map, hash table, or dictionaries. Now in Python, there are several kinds of dictionaries. In Java, there are several different kinds of hash maps. So there's no like one flavor. Sometimes the programming language will remember the order that you put things into the hash. So when you say, go get me the list of keys, it'll actually give you those keys back in the order that you put them in the hash in the first place. So even if I put like Grayson in there first, and then I put Max, and then I put Aiden, and I say, go get me a list of those students, it would give them back to me in that order and not necessarily alphabetical. Some programming languages, it would actually go look them up based on the hash value of the name. And so it comes back out in what appears to be a random order. So there are lots of variants, and those variants exist for different kinds of reasons, which we don't really have time to go into. What is it good for? It's good for finding things based on a name. So you don't have to remember a position anymore, and it's a very, very fast lookup. It's pretty much as fast as knowing the index of an array. Not always, but it's extremely fast for looking things up. What is it not good for? It uses a lot of extra memory. When you think about it, we've got a whole computation that we have to do, and that computation has to balance between uniqueness and speed, because the more unique it makes something as a representation, the slower it takes. And we need our hashes to be fast. Like when we're writing lots of code, we need that hash to be really, really quick. And so it's not very good at memory because it's also an array of linked lists. And so the array has to be all what we call contiguous in memory. It's like our housing development where all the houses are next to each other, but then each of those is a linked list where things are kind of scattered all over memory. So it's using a lot of memory to store what we think of as just a key and a value. And then that value could be another hash. Actually, in Ruby, the key could also be a hash if we want to. In Python and Ruby, any kind of object can be a key. But generally, we want to keep those keys really simple. And so strings, symbols, and numbers are the best things to use as key values there. It is built into Ruby, but if you had to build it yourself, now that you know how arrays and linked lists work, you could go build your own hash, and you could build your own methods of like, go get this value for a given key. And if I don't have a value, give me back a nil, for example. So when we say, make a hash with curly braces in Ruby, it defaults the value to nil. So if you try to look up a key that's not there, Ruby will give you back a nil. You can override it and you can say, I want to set a different kind of default value, like a true or a false or something like that. If you want to, we can talk about that another time. And then as far as technical challenges go, like I said, arrays and hashes are going to be the two top data structures that you're going to use in most technical challenges. And there are plenty of them. We're going to cover one of them in class tomorrow in the Big O class, probably. I like to give students the choice of what kind of technical challenge they want to look at. And sometimes choosing a hash is a good answer. And the algorithm that you come up with to solve the problem is actually better served with a hash. Sometimes it's worse if you choose a hash because of how you're storing things and how you have to look things up later. And we're going to go into some of those examples tomorrow about like when you want to use a hash and when you don't want to use a hash. But again, kind of the overall theme, and I know we're over time here and I appreciate your patience. The overall theme here is like knowing what is this good for? What is it not good for? Will help you decide when you want to use that as a tool. And being able to contrast these kinds of things. Because sometimes on a phone screen, you could get asked like, when would you use a linked list over an array? When would you use an array over a linked list? And you could talk about things, well, a linked list can insert in the middle, but an array can't. But an array, it's way faster to just seek to a position where you can't in a linked list. So by knowing that kind of information now, you have a better answer for that. And so again, you don't have to be experts at it, but at least knowing that the information is there will be really helpful. If you've got the time to study and read up on some of the stuff, I definitely recommend it. Cool. Any questions on hashes that I can answer? Otherwise, we got PD work time. Yeah, Sam, what do you got?
So like you mentioned, hashes to retrieve or the value using the key is mostly, majority of the time, O of 1 constant time, because you're able to. So it's an array of linked lists. And the way I imagine it is that I still understand why still O of 1 if we have to iterate. Like, are we iterating through that array to find the values of the heads?
Yeah, good question. So I forgot to mention that. So when so let's say we take Sam and Sandra's name. And that tells us which bucket it's going to go into. When we run the key through the hash algorithm, it's just giving us like a numeric reference of some kind, and it's usually really big. But our programming language of choice is probably only giving us like 1,000 buckets or maybe 10,000 buckets. And we call them buckets, but it's really the size of the array of linked lists. And so what we do is we take this really large numeric representation and we use the modulo operator, we mod that by the number of buckets that we have. And so if we have, 1,000 buckets, we take whatever that representation is and we say, okay, well, mod that by 1,000. That tells us which bucket that we're going into. And so we can immediately seek to that position. And so again, it's like one math operation to calculate that big number. It's another math operation to do the modulo. It's another one operation to then seek to that position in the array. And then if there's no collisions, we've got one lookup then to say, what's the value of the start of that linked list? Oh, hey, this is what I'm looking for. I'm done. And so we say, well, because each of those only took one step, then it's really it's a one-step operation. But because in Sam and Sandra's case, there's a collision, that linked list now has multiple entries in there. Now we have to iterate over that linked list potentially to look to find what we're looking for. And that's where it's no longer O1 lookup or constant time lookup.
Cool, thank you.
Yep, thanks, Sam. Cool, and we'll get into like what is O1 and ON, and we'll talk about that stuff in the Big O notation class tomorrow. Cool. Well, thanks again for helping out. Definitely make reference to that document and read through it over time if you can. I think it's really good study material. I don't recommend like reading absolutely everything on Wikipedia, but if you can kind of glean like what's it good for, what's it not good for, where's it commonly used, that's going to help you solve a lot of technical challenges for interviewing. And then if you can find good technical challenges for each of those data structures, add them to that document. That would be a really good way for other people to practice those things as well. Cool. I appreciate your patience going a little overtime. We got PD work time for the next little bit. Please make use of that time. If you do have questions about PD stuff and you want my input, I'm happy to do so. Just go ahead and DM me. I'll be at or around the computer. But I'll be away for lunch. So cool. Thanks, everyone.